table a little bit more, I would like you to choose, or I will choose, a problem from this set, 35 through 38. And I'll explain what that means. It's basically practicing this table.
37.
That was exactly what I was going to say, but you said it before me. Okay, very good, 291. So I'm going to copy this. This is total gibberish. It doesn't mean anything. I look at this and I have no idea what it means. We will clarify everything in a blink. F prime of 0 is 0. F double prime of 0 is less than 0. F of 0 is 5. F prime of 2 is 0. F double prime of 2 is greater than 0. F of 2 is 2. Okay, what else? F prime of 4 is 0. F double prime of 4 is less than 0. And F of 4 is 3. Gee whiz. So the question is, sketch a graph that has all these characteristics. Of course, there is more than one correct answer. This means nothing to me. Everything will be very clear in a blink. F prime of 0 is 0. Done. F double prime of 0 is less than 0. Done. F of 0 is 5. Done. F prime of 2, F prime of 2 is 0. Done. F double prime of 2 is positive. Done. F of 2 is 2. Done. F prime of 4, F prime of 4 is 0. Done. F double prime of 4 is negative. Done. F of 4 is 3. Now there is light, complete light. Okay. Obviously, because the first derivative is 0, these are critical numbers. These are the values of y at those critical numbers. So the point 0, 5, one, 2, 3, 4, 5, the point 2, 2, and the point 4, 3 are very clear. Now, what type of point is 0, 5, knowing this? When the second derivative is negative, the function does not hold water. It's concave downward. So what do we know about 0, 5?
The maximum?
Absolutely. Thank you. Good. Now, what do we know about 2, 2? Knowing that the second derivative indicates this shape for the function. And knowing that 2 is a critical number. Otherwise, I can't conclude. Knowing that those are critical numbers, 0, 2, and 4, and because the first derivative is 0, and the second derivative says this, then I know what they represent. But both conditions have to be fulfilled. They are critical numbers, and I know the shape of the graph based on the second derivative. So then, 2, 2 is what? 4, 3 is what?
2, is a minimum.
Excellent. And 4, 3.
Maximum.
Very good. So that's what we have to graph. Make sure that this one is a relative max. Then there is an inflection point somewhere here between these two. Okay. Here's my inflection point. I can add whatever I want, but these have to exist in my graph. I added an inflection point. I show that this is a relative minimum. I show another inflection point. I show that this is a relative maximum, and I continue the way I want. You can turn it, whatever, it doesn't matter, as long as this is the maximum, this is the maximum, and this is the minimum. The rest, it's up to you. The sky is the limit. We're asked to present a function that has the relative max here, the relative min here, and the relative max here. The rest, it's up to you. So this was a typical example for practicing the table. Any questions on this? Okay, you can always stop me, you can always interject, please. I'd like to look at a word problem, so we can move on. Gotta have it device is introduced in a market with such and such potential buyers. We're given the sales function, total sales in millions, X months. Find the point of inflection and interpret its meaning in terms of the rate of change in sales. Before we do anything, can anyone tell us what, when we talk about the rate of change in sales, what are we really talking about? The rate of change in sales. What do we talk about? Rate of change in a function. Let's say the function is f of x. Is, what is it? Sorry, I should have stopped. So that's my first question. We need to clarify this to make sure we're on the same page. The rate of change in any function, let's say a function f of x, is, what is it? We talked about this several times. We calculated it millions of times already. When we say the rate of change of a function, what are we referring to? Please try. What did we say the rate of change of a function is? And we calculated it in two different ways, with a definition and then with formulas. What is it by definition? The rate of change in a function. Anyone, please?
The slope of a tangent line.
In other words, the derivative. The slope of the tangent line, indeed. Or the derivative. Same thing. Both of them are the same. Excellent. Thank you, Matt. Indeed, that's what it is. So when we are asked to find the point of inflection and then interpret it in its meaning of the point of inflection in terms of the rate of change in sales, they are asking us to connect the point of inflection to the derivative. The derivative is the first derivative. The point of inflection is given by the second derivative. So let's take a look. So we have S, so this is problem 41 on page 290 something, 91. So we have S of x equals negative 0.0131 x cubed plus 0.661 x squared minus 2.021 x and plus 6.865. So I take notes, millions, and x is in months. Good. Find the point of inflection. Fine. So what do I have to find first? What do we need to determine first so I can get to the point of inflection? What do I have to determine first?
The derivative?
Yes, of course, the first derivative, indeed. So negative, so this is 0.0393 x squared plus, this is 213, how many digits? 1.3x minus 2.021. Perfect. I found the first derivative. What do I need to find next? In order to find the point of inflection, I need to continue with?
The critical number?
No. Very good point. So I find the critical numbers only when I'm interested in finding max min. But we're not interested in finding max min. We're only interested in finding the inflection point. So what do we need to determine next? Otherwise, yes. I would have said yes, the critical numbers will be next. Correct.
The second
Of
derivative?
course. We need to get to the second derivative. Thank you very much. So this is 6. This is 8. This is 7. 0. X plus 1.322. Excellent. So I have the second derivative. What do I need to do now in order to find the point of inflection? This is similar to the critical number. So I have to set it equal to 0 or to undefined, which is not the case because it's a linear function. So when I set it equal to 0, when I set this equal to 0, I get x equals, when I move it, 1.322 over 0.0786. I don't know what that is. Um, 1.322 divided by 0.0786. Good, so 16.82. So x approximately 16.82. Good. Now, the function value s at 16.82 is a number. We have to plug it in. I don't know. We have to calculate this with 16.82 in it. So the inflection point is 16.82 comma s calculated as 16.82. So this is the inflection point. Now, when we study the sign just of the second derivative for a second, so we're talking about months. So I cannot have, although it's a polynomial function, I can have 0 to infinity, but not negative. So 16.8 is here, and this is 0. Now, if I plug in 0 here, I get positive. And on the other side, if I plug in 20, I get negative. So it's coming from opening upward to opening downward. The question here is also, what is the connection between the inflection point and the first derivative? And I like to explain this concept. So it's opening up, it gets to the inflection point, and then it's opening down. This is how the function looks like around 16.8. I'm only focusing on this point, 16.8 comma, the function value at 16.8. Well, they're asking us what really, this is the graph. Just this portion, I'm not interested because they're asking us, connect the inflection point to the first derivative. So here's what happens. See, initially, the first derivative is negative, big negative. Then it is smaller, but still negative. Then it gets to 0. But then it's positive, and then it's positive, and then it's positive, and then it gets to 0 again. So what really means is that f prime of x, the rate of change, x s prime of x, near this point is increasing, right? It's coming from negative, and then it becomes positive. So increasing. But then the manufacturer has to be careful because eventually it will peak and the first derivative will not increase anymore. But this is what the first derivative does. It's coming from huge negative, 0, and then it becomes positive around the inflection point. So that was the idea. So the inflection point changes, it showed us where the function changes concavity from opening upward to opening downward. Any questions? So then they were saying here, graph this on 0 to 30. So I would not bother with all these numbers. I will just look at a graphing calculator between 0 and 30. So we can do that. But that's what's going to happen between 0 and 16.8, and then beyond 16.8 to 30. Okay, I would like to continue. Let's see.